All right, so today we're only going to get through calorimetry, and we're going to stop, and we're going to do a demo and practice a bunch of problems. For this week, my intention was to do lab tomorrow, but based on how block 2 went and just how much practice we got in, I feel like you would come into lab and be confused still and not quite sure how to handle it, and then I'm going to have to just coach you through the entire lab, whereas I'd rather you do the lab, understanding how calorimetry works, and solving the problems on your own. So we are going to practice calorimetry tomorrow using lots of free response questions. I will help you with all of your homework problems if you didn't get those. We're just going to practice a lot of calorimetry tomorrow. And then Monday, you know that I'm out, so you're going to take your quiz without me, with your substitute. You have a half day. So you should be able to review a little bit and then take the quiz with your sub. I completely trust you guys not to cheat, right? And if somebody's cheating, I'm sure one of you would tell me. So we're just going to take it. You don't need my help anyway to take a quiz, so you're just going to take the quiz on your own.
So the quiz is Monday?
Quiz is going to be Monday.
So do we have any other tests or reasons the rest of the week?
No, then Tuesday and Wednesday we are going to do the lab. So the important thing for prepping for this lab, though, is that you understand. So I'm going to give you the lab tomorrow so that you can start reading through it and prepping for it, because Tuesday when I come in, I cannot spend a half hour of time telling you what we're going to do. So we might use a little bit of time tomorrow just so that we can talk about the lab so you know what to expect, because we only have half days. So the second you come in, you need to be doing your lab. You're literally going to be mixing 2 solutions. You're going to put solid in one and solid in another and dissolve them and measure temperature change. And that should take you no more than an hour to do. But if you have no idea what you're doing, you're going to ask me a million questions about how everything works, and we're not going to be able to get through it. So then my intention is on Wednesday, I can start doing the practice problems, the post-lab questions with you in class, assuming that we finish lab on Tuesday. And then you could take that home over Thanksgiving and work on it. So calorimetry is the hardest part about enthalpy, delta H. It's because it's just experimental data. So when you look at the questions, you don't get a nice little table of values that you just add and subtract. You actually have to work through the experiment and figure out what the information being given to you means. So we're going to spend most of our time on calorimetry, and the AP exam really does, almost every single year, give a calorimetry question in some format. It might not be the entire question, but it might mention something about it and then go to something else. And then we'll do Hess's law and enthalpy of formation after Thanksgiving. Wrong one. All right, so these are the 4 ways that you can find enthalpy. Yesterday we did bond enthalpies. And remember, even though I showed you the equation for doing products minus reactants, that's really not until we get over here. So right now, the only equation that you possibly could be using to find enthalpy is just bonds broken minus bonds formed. That's it. So now we're going to do calorimetry, then these 2 we'll work on separately. All right, calorimetry is the measurement of heat transfer. This is sort of helpful and useful information. When you think about calorimetry, this is what I want you to envision. It's literally an insulated environment, like a closed system. So we are going to use an oversized coffee cup. In the years past, I've literally just brought coffee cups to do the experiment, but you guys are just so aggressive with them that you break holes through the bottom and the tops, and it just doesn't work out as well. So these were literally $20 each through my science catalogs. But I think they're worth it because this lab most often makes people frustrated because their data is skewed, because they lose heat to the surroundings. So a calorimeter is just a closed system that measures the amount of heat transfer from the reaction that's taking place inside into the surroundings, which will be the solution in here. So we're going to put water in here. We're going to dump some solids in. We're going to close it up quickly. And we're going to make 2 holes, one for a stir rod and one for a thermometer. And I'll show you sort of the setup in a picture in a little bit. And then you're just going to measure temperature change. But the issue is that this isn't a closed system. There's surroundings around it, right? And so we could lose heat to the surroundings just because it's not really that sealed off. So the important things will be to make sure that your hole for your thermometer and your stir rod are really small so that no heat is escaping. And then obviously not to break a hole through the bottom of this as you're trying to stir it and mix it all up. So this is technically a calorimeter. And so it's literally like an insulated coffee cup. And in fact, some really dorky people like myself and others will call their coffee cups calorimeters. So like 2 years ago, I got a Christmas gift from a student with our pictures all on it. And then she wrote on my tea mug, like my insulated cup, De Bruyn's calorimeter, because that's what it is. It just keeps things insulated so that you can measure temperature change. Another word that they use is they will call it a coffee cup calorimeter, or they'll call it a bomb calorimeter. So if you see some of my free response questions I'll give you, it may call it a bomb calorimeter. That more or less is just a much better system than this, and that's how they will measure heat transfer. Also, on a side note, we use calorimetry all the time in food science to determine calories. Do you get the word here? Calorie and calorimetry. Calories are just a form of energy, and there's a conversion factor to get us from calories to joules. We use joules now, but like prior to 1999, the AP exam almost always used calories and kilocalories. So when you look at your food package and you see calories, that's an amount of energy, right, that food source will give you after you eat it. So you eat that food, that's the amount of energy that's going to be released into your system, and then you get to use that energy. So the way that they measure that is they take the food, so pretend we're getting a Cheeto, right? We take our Cheeto, we place it in our bomb calorimeter, and we burn it, and we figure out what the heat transfer is to the surroundings. And that amount of heat transfer tells us how much energy that piece of food had in it. And then we can calculate calorie content using calorimetry. You like that, don't you? Yeah. So that's what we're doing. We're measuring temperature change from whatever we're doing on the inside of the system. So we talked already that we can't measure heat directly from our reaction because you can't stick a thermometer into that little molecule determining what happens to it. So the only way that we can measure temperature changes are from our surroundings before and after a reaction takes place, right? So like if I'm burning my Cheeto, the initial temperature of the surroundings is one thing. I burn that Cheeto and energy is released to the surroundings. Now I can figure out how much energy is released, and I can figure out how many calories were burned. So we always are going to be measuring the surroundings and not ever going to be able to measure the system itself. All right, here is your equation that we're going to use to determine how much energy is occurring in or out of a system. And it's called the delta Q equation. They use specific heat capacity to figure this out. So this equation is given to you on your sheet. It just says, though, Q equals MC delta T. So when we are calculating this, we need to recognize that there are two Qs for my system. There's going to be the Q that the reaction is releasing or absorbing, and the Q that the surroundings are releasing or absorbing. Because remember we talked about that they're equal but opposite, right? So whatever happens to my surroundings is going to be the opposite of what's happening to my system. So in this equation, I have delta Q, which is the amount of heat that's lost or gained by a substance. Mass is M of that specific substance. And the specific heat capacity is a measure of how much energy it takes to make 1 gram go up 1 degree Celsius. So everything has its own specific heat capacity. So water has a high specific heat capacity. Iron has a low specific heat capacity. Iron will heat up quickly and lose heat quickly. But water takes a lot of heat to get it to go up 1 degree. And then delta T is temperature change. We always, anytime we do delta anything, it's always final minus initial. Always, right? So we're going to measure the temperatures before and after. So this sentence is important for you to understand what C is. It is the amount of heat, joules, the unit is joules, per, and we're going to do 1 gram, raising it a degree, well, raising it a Kelvin. But this can be changed into just degrees Celsius and use the same number for the specific heat capacity. In fact, all of your questions will give you the temperatures in degrees Celsius, and you just use the specific heat with the degrees Celsius in the unit. So for water, it's 4.184. For iron, I think this was iron, it's 0.45. So this has a very small specific heat capacity. In other words, the temperature change is large here, and the temperature change would be small here for the same amount of energy for both of these, right? If I supplied 1,000 joules to both of these, this temperature would go up much faster, higher, and the temperature would go up less because this specific heat capacity is much larger. Do you understand that? If I say 1,000 joules of heat is being supplied to water, 1,000 joules of heat is being supplied to iron. This temperature goes up less than this one. All right, so we're going to use the delta Q equation to find how much heat is released or gained for a specific reaction. So I'm going to write something down that is incredibly important for you to understand. We calculated delta H yesterday, right? Delta H is enthalpy, so is delta Q. To adjust this. So delta Q is always going to be for random quantities used in a reaction. In the lab, like you determine how much you're going to put in a reaction in the lab. So you determine this in lab. When we say delta H, it's still heat. It's still enthalpy of a reaction. However, this is the amount of heat for 1 mole of substance. We find this from the balanced chemical equation. So yesterday I put up on the slides, it gave you the amount of energy that was released when we formed water from hydrogen and oxygen. So I'm going to explain this in terms of that equation. If I have hydrogen gas and oxygen gas react to make water, and then I balance my equation here, this released, I gotta look it up. This released negative 572 kilojoules per mole of water that was formed. So if I take instead the same exact reaction, but I use 1 gram of water, 8 grams of oxygen, and I form 9 grams of water, this is delta Q, because it's a random quantity, and this amount of heat release is negative 143 kilojoules, not per mole. This is delta H. Do you see the difference? How many moles did I start out with of of hydrogen? You actually do stoichiometry here. Like, we're not guessing. How many moles of of hydrogen did you start with? So, like, let me remind you, because this is so simple, you almost can't do it at this point. Molar mass goes down here. Hydrogen is 1, so it's 2.0 grams of H2 equals 1 mole. Doesn't it seem really hard to do that? So 1 divided by 2 is what? 0.5 moles. So technically I'm starting with 0.5 moles here, right? But I started with 2 moles for this one, for the balanced chemical equation. So this produces negative 572 kilojoules, but 0.5 moles produces negative 143. That should make sense to you. Yes?
Why is that, since you have 2 moles in the first one, why isn't it that you have 1 mole?
Because I wrote 1 gram.
No, on the top.
I wrote 2 moles.
You said there's 0.5 moles in the top?
No, here.
Oh.
Here. Because this is the random quantity. Now, had I started with 2 moles of this, then it would produce that much heat. And we talked about this yesterday. Like, if I use more fuel, I produce more heat. Remember, we talked about this when we were heating our house, right? So using more fuel is using more grams of it, so I would produce a greater reaction, and I would produce more heat. Well, if this is my example and I use less moles of it, well, I produce less heat, right? Q is your random quantity. Q is what you do in the lab. You take a certain amount of stuff and you throw it in a pot and you mix it all up, and now you get some sort of heat exchange. So if you choose, Maddie puts in 1 gram and then Gonzo puts in 1,000 grams, we should clearly see a different amount of heat being released, right? And that's your Q. Each of theirs is their Q. But delta H is the same for every balanced equation. This is always going to be true for this balanced equation. Do you understand that? So you're going to have to calculate Q's throughout this lesson and then translate it to a delta H, which is just a simple ratio. Like if that's the amount of heat for 0.5 moles, then what's the amount of heat for 1 mole? That's what we're going to go to in a balanced chemical equation. Obviously in this one, it's for 2 moles, and if I wanted to do it per 1 mole, I would divide that answer by 2. Agreed? So it's for the balanced equation. If they represent it to you balanced and they tell you that's the amount, then in this example it would be worth for 2 moles. If I wanted to find it for 1 mole, I would divide that by 2. So very important that you recognize Q and H are very different in the sense that they're representing 2 different amounts. Okay? All right, so here's my coffee cup. And we call it a coffee cup because that's technically what it looks like, but it's a calorimeter. And so my calorimeter doesn't necessarily look like a coffee cup because it's much larger. In our system, though, we're going to end up, instead of using a stir stick, I have what looks like, you know when you dye Easter eggs? It's like a stick with a little hole on it. We're going to use that. That way you're not going like this, which then means that you're making the hole on the top bigger. We're just going to go like that to try and get it to mix by going up and down. Then you're going to make a little slit for your thermometer, and it's important that your thermometer never touches the sides here. Why? Right, because then you're really just measuring sort of the calorimeter. All right, so let's talk about what our surroundings are. When we do this reaction, we want to measure our surroundings, right? Because these little molecules in here are the systems. So I want to see what the surroundings are doing, not what the system's doing, right? If I measure the surroundings, then I can determine what the system itself is doing. So what part of the surroundings do I want to measure? These little dots are the system. So if they're doing something, the liquid. So we're going to assume that this is water. When we do most of our experiments, and most of the ones that you're going to read, they do them in water. That's the simplest thing to do. So we want our surroundings to be the water or the solution. SOLN is solution, okay? So that's really what we want. We want to measure this. Because if I know that the temperature of the water is going up, then I know that the system is releasing that to the surroundings, right? However, I have other parts of the surroundings that I do not want to measure, and we need to talk about those. Those are part of your error analysis anytime that you're doing a lab with calorimetry. So what are the parts of the surroundings that I don't want?
The air.
Okay, so there's air, like above it in the cup, right? So the calorimeter, which is the styrofoam part, right? So the styrofoam. What else? One more thing.
The stir stick?
We could say that. I didn't consider that, but sure, we could say. So now there's another one. The sticks and the thermometer, because we don't want to measure those. What else? Why does my tea get cold every morning and I get so disappointed on that last sip? What? What are my hands part of? It's like a big word that we used yesterday that starts with a U. The universe. The rest of the universe is outside of this, right? Which includes my hands, includes the air, includes everything around this. So the universe, the air, the styrofoam, the sticks, and the thermometer all are basically interference, right? They're all going to cause error because heat can be lost or exchanged through those objects or through that. But we want just our solution to be measured. Oops, wrong way. All right, so whenever you're doing this, just recognize that there is a source of error. And sometimes they will ask you that. In the lab, I will ask you that. I will want to know what's a possible source of error, because you'll see what it should be and what it isn't, and you'll have to justify it. And your justification is just that it's lost to all these other things, right? Heat could be lost, or heat could be absorbed from those things also. So we're really looking at just the water temperature going up or down, and then if we know what happens to the water, then we can determine what happens to the reaction, right? All right. When measuring the heat lost or gained in a chemical reaction that takes place in a calorimeter, again, it could say coffee cup calorimeter or it could say bomb calorimeter, we use the solution as the basis for our calculations. So we are, again, not measuring the reaction, we're measuring the solution. So this would say delta Q of the solution, mass of the solution, C of the solution, delta T of the solution. We often will use the specific heat capacity of water because when we do a reaction in water, like say I mix, I throw in sodium chloride and it dissolves. We say sometimes that's a chemical reaction. Well, that amount of sodium chloride and the reaction there is negligible to the amount of water that's going to be in there. So we really take into account just the specific heat capacity of the water. And the questions will often say, assume that the solution has the same specific heat capacity of water. So then you just use it. And they will give this to you because it's not in your equation sheet, so they have to tell you what specific heat capacity to use. All right, so we're going to measure everything for the solution, but then we need to compare that to the reaction. Let me just look at the next slide. Okay, I'm going to write this down here. So if my solution, delta Q of the solution, if the temperature of that solution goes up, so think about this. I'm just going to jot numbers down. It was 10 degrees, and then it goes to 20 degrees. So the solution temperature goes up. Is that endo or exo? Endo, right? Because for temperature to go up, it has to absorb heat from something, right? Like if you're heating water in a pot, you're heating it up by giving it a source of energy, your flame, right? So the water is absorbing the heat and the temperature goes up. So this is an endothermic process. Temp goes up, it would be positive, right? Goes up. I'm writing these things down because that's common sense to you. And when you read a problem, you should use common sense first to solve. I came up with this little phrase, not purposely, in block 2, but I said, be smart before you start. It's like, oh, that's great. Because you need to figure out what your signs will be, because if you make a calc error, you're just going to go with it. But you can figure this sort of stuff out in advance, knowing that this is supposed to be endo if my temperature of my solution goes up. So if the solution is positive, then what must be true about delta Q of the reaction? That is why we put a negative sign. They don't give you this equation on the equation sheet, but this is common sense because you understand thermodynamics now. So if I calculate delta Q of the solution inside the calorimeter, then when I want to find what the delta Q of the reaction is, it is equal but opposite. Because where does the heat come from if it went from 10 to 20? The surroundings. No, these are the surroundings. If the temperature went from 10 to 20, the water are my surroundings. Didn't we just write that all over here? The water is the surroundings. The temperature goes up. That's endo. It's taking in heat from where? The reaction. So then the reaction is what? Endo or exo? Get that? It has to be releasing heat because the water is what's the temperature change is occurring in the water, and those are my surroundings. So if it went from, if this is my solution, went from 10 to 20, it's endo. That means that the reaction gave up heat, so water temp went up.
So that's exothermic.
The reaction would be exothermic in this little example that I'm giving you.
And why do you have endo?
This was the solution. If the solution's temperature goes up, Tyler, it's an endothermic process, right? Which means that it's getting the heat from the reaction, so the reaction must be giving it to it. So like take this for example again, here's my calorimeter, here's my water, here's where my reaction's taking place. The reaction, water is at 10 degrees, heat comes out of the reaction and goes into the water, the temperature of the water goes up. Agreed? If I have this occurring, and it's going into the reaction, then the temperature of my water goes down. So this is important for you to understand, that the solution's temperature change will result in either going up or down, which will tell you in advance, before you even start the problem, what delta Q of the reaction is doing. Because you'll know what delta Q of the solution is doing. Agreed? So be smart before you start. All right, we are going to look at solving a few different types of problems. This is just reiterating what I just said to you. Hey, even I heard. You're driving now. That's great news. But let me pause so we can talk. Okay. So this is exactly what I just said. It says that the reactants and products are the system. We can't measure that, so we have to measure the surroundings, which is going to be the water. And the heat lost or gained by the solution is equal to the heat lost or gained by the reaction, which is why this equation makes sense. Is that they have to be equal but opposite, because one thing's going to absorb the heat and it's coming from some other spot. If you calculated the delta Q of the solution to be 568 joules, that means that the temperature of the solution went up, so it's endothermic. The solution gained heat. This means the reaction was exothermic. Because in order for the solution to be endo, the reaction has to be exo, right? And so therefore the delta Q of the reaction is negative 568. So every time that you do these, you will solve for delta Q of the solution, and then you will naturally solve for delta Q of the reaction, and delta H is always for the reaction. You never are solving delta H for what happens to water, right? When I do this equation over here, this is delta H for this reaction, not for what happened to water if it goes up or down, the temperature goes up or down. So you're always going to calculate delta Q for the reaction. So we're going to solve two different types of problems today. There are three types of problems that we're going to do. So they will ask you a variety of calorimetry problems, but there's always only sort of three. So are you ready to listen to them without looking at this problem? One of them is a hot piece of metal goes into water. So if a hot piece of metal goes into water, the metal itself is the system and the surroundings are the water. Okay? We can see that system, can't we? That's like me holding hands with someone who has hot hands and I have cold hands. I can see and feel, in a sense, that system. One's the system, one's the surroundings. Which one's the system in my hand-holding example?
You.
The hot hand. Because the cold hand can't transfer heat in or out, right? The hot hand is the only thing that can give the heat. All right, so the system and the surroundings for this example that we're going to do, the metal is the system, the surroundings is the water. The other example is going to be taking a solid and dissolving it in water. So I take an actual solid, like 10 grams of sodium chloride, and dump it into water. And I measure what happens. So in that case, that's dissolving, but I'm going to ignore the fact that that's even dissolving. I'm not going to take into account that solid, in a sense, like I would for the piece of metal. And then the third type is going to be when you have two different solutions and you mix them to make a precipitate. So I have solution A, solution B, they get mixed, the volumes are additive, and I calculate transfer of heat. Okay, those are the three types that you will typically see. So this problem is using the iron bar. It says a 97-gram iron bar was heated to 143 degrees Celsius and placed in a coffee cup calorimeter containing 350.0 grams of water at 25.00 degrees C. The maximum temperature of the water was measured to be 28.40 degrees Celsius. So let's draw a picture. I would suggest on any of these problems, if you're getting confused, that you draw yourself a picture. So I have a calorimeter of water, and this is at 350 grams, and it's at 25 degrees C. And then I dump in this piece of metal here that has an initial temperature of 143 degrees C, and it's 97 grams. The temperature goes from 25 to 28.40 degrees C. So be smart before you start. Tell me what is happening to the solution. Yeah, it's getting hotter, but what about it? Absorbing heat. So what should my value be?
It's gonna be positive.
Yes. So before I start, I'm going to tell myself delta Q of the solution is positive. And where is it getting the heat from?
The surrounding.
No.
Wait,
The
what
water
is
is the surrounding.
Oh,
System.
What is the system in here?
The iron.
So my delta Q of my iron, which is the reaction, you can just write reaction, is going to be negative because it's giving up the heat. Do you understand that?
Yes.
The iron bar got dropped in here. What's the final temperature of the iron bar? 28.4. Why? Because you reach thermal equilibrium. That's why on your Quizlet, I made all of you draw that when they come into thermal contact with one another, velocity vectors are really high, velocity vectors are low, and then they reach equilibrium when it's all over, right? So I drop in a high velocity vector into water, they come into thermal contact with one another, and eventually they reach thermal equilibrium, so this is the final temperature for both of them. Agreed? And then the last thing I'm going to ask you is which one has a higher specific heat capacity, the water or the iron bar, just from the data, not from the slides that I gave you earlier. What are you looking for? Because you will get questions like this as multiple choice. Which one has a higher specific heat capacity?
No water.
Because higher specific heat means less temperature change, right? Because that energy is going to be used to heat up the water that 1 degree. So look at the temperature change that happened from 143 to 28 compared from 25 to 28. So this has a very low specific heat capacity because the temperature change is more drastic. It happens much more easily than it would with this. So the amount of energy used to go from here to there is much smaller than the amount of energy to go from there to there. So water specific heat capacity is high.
What did you say when you said that something has a higher specific heat capacity, it means what?
The temperature change would be less. Right, because specific heat, when you go back and look at your notes, the definition, because of the units, is the amount of energy, joules, that it takes to raise 1 gram of that substance 1 degree. So if it takes a lot of energy to raise it 1 degree, then it's going to have a small temperature change for the amount of energy released. Okay, so my question says, how much heat was gained by the water? How much heat was lost by the iron bar? And what is the specific heat of iron? So you know, all you're going to use is your delta Q equation that you saw in the previous slides. And I'm going to leave that here for now so that we can go back to what we initially thought the answer should be. So how much heat was gained by the water? Delta Q of the solution. They will write water. I always write solution and reaction. Solution and reaction. I just think it's easier to stick with that. So you're going to plug this in for all the water components. So delta Q of the solution is equal to M of the solution times C of the solution times delta T of the solution. What's the mass of the water? 350.0. Didn't it say 0? Grams. Why do I want that? Sig figs. Okay? C is the specific heat capacity of water. This question should have given you the specific heat capacity because they always will. But you have to go back and look at your notes.
Bless you.
Thank you. My units are joules divided by degrees Celsius. And then I'm going to do temperature change. So it's 28.400, 40, right? Not 00. Minus, and the original temperature was what?
25.00.
25.00 degrees Celsius. So just take a look that your units are canceling. Look, degrees Celsius cancels with degrees Celsius in the denominator, grams cancels with grams, and I'm left with joules, which is what my answer should be reported in. Not joules per mole, just joules. So now you solve. Get your handy dandy calculator out. So the reaction is endothermic, which we already said, didn't we? We knew it should be positive. So if you got the wrong answer here, and you got a negative value, you would know that you actually calculated something wrong because you figured it out before you started. So if this part is endothermic, then how much heat was lost by the iron bar? Negative 4,979, right? Because how else would it have gotten that heat? It had to come from the source, from the iron. So your questions on homework and sometimes on the free response, they will ask you to justify if energy was conserved. So the question will say, was energy conserved in this process? And the answer is obviously always yes, due to the law of conservation of energy, right? But the justification is, and this is what you will say, the heat gained by the water is equal in magnitude to the heat lost by the iron bar. That's always what you're going to say. If it's for whatever solution and whatever reaction, you will always say the heat lost or gained by the solution is equal to the amount of heat lost or gained by the reaction. That's always the answer for the justification. Ashley, I think what you're doing is least decimal places first, and then using it to multiply, which would then have 3. Is that what you're saying?
Yeah.
That's true. So problems like this are tricky to grade sig figs for, because what she's pointing out, and I think you should all recognize this, is that you initially do a subtraction problem, and when you subtract and add, you have to use least decimals. So this comes out to 3.40. That only has 3 sig figs. So technically, if you take that answer and multiply it by these, then your result should only have 3 sig figs, and I think that's what you're pointing out. However, hold on. When you do these problems, there is lots of areas to round for sig figs. Sometimes people round at every single step. But if you do that in reality, if you really do that when you're like in a lab situation, your answer is going to be really off from where it should be if you're doing multiple calculations, right? So common practice, although it's not a rule, is that you typically round at the end for sig figs from all your original data. And the idea here too is that my thermometer can measure 4 sig figs, so I'm going to carry that through in my result when I'm solving at the end. But if you put your answer down with 3 sig figs, I wouldn't take off for it because I know exactly what you're doing. You're following the rules that you're supposed to follow. Yes?
So we can do either?
In this situation, yes, that would have to happen, right? But I'm telling you right now, don't do that. Like, keep the original amount of sig figs because my thermometer can measure 4. So just carry the 4 through because the original data has 4 sig figs. Okay? I'm asking you to do that. Although if you rounded for 3 and you had that justification that Ashley did, then I'm not going to argue with you because that's true. All right, what is the specific heat of iron? So I'm looking now for C. I know delta Q of iron, don't I? I know the mass of the iron, but I'm looking for C of the iron. This is the piece that I'm looking for. And I know the delta T of iron. So you're going to plug it all in and do some algebra. Your sig fig answers will round a little differently than if you were to just use the number directly in your problem. Because I gave you the specific heat capacity early on, you should already know what your answer should be. So you get 0.45 joules per gram degree Celsius. How many of you got that? Yeah, I mean, you're literally plugging in numbers, right? At this point, what was your delta Q of Fe, of iron? Negative 40,979, right? The mass of the iron bar was told to you to be 97 grams. And the temperature change went from final, maybe this is where you made the mistake, final minus initial. T final is 28.4 minus your initial. So you plug that all in your calculator. So if I'm using my calculator, this is how I'm going to do that. I'm going to type in negative 4979. I'm going to hit the divide button, and then I'm going to use parentheses, and I'm going to write 97, and then I'm going to hit multiply, and then I'm going to use parentheses again, because I'm just going to let my calculator do all of it for me, and I'm not going to write anything down, and then close parentheses on the outside, and I will get the right answer. You should avoid writing things down over and over, because there's a good chance that you're going to get a transcription error, right, JC? Good chance. Okay. So, next problem. This is the other type, right? This is what I was describing before. The third one is when you have two different solutions and then I mix them together into a beaker and I form a precipitate. So let's read this one. When 20 milliliters of a 1 molar sodium chloride solution at 22 degrees C is mixed with 20 milliliters of a 1 molar silver nitrate solution at 22 degrees C in a calorimeter, a white precipitate forms and the temperature of the mixture reaches 29.6 degrees C. A lot of information, right? So I'm just going to draw myself a picture. I have beaker 1 and I have, where's my orange one? And I have beaker 2. Let's change that line to be here and here. So this is 20 mils, and this is 20 mils, and I take this and I dump it in here. So now what's the volume? Right. Okay, this is going to add, the volumes are going to add, and that's what this is going to tell us. It says, for this whole problem, here's a whole sentence about assumptions we're going to make. First thing is we're going to assume that the specific heat capacity of this mixture is the same as water. Why? Because how else do we make molarity solutions? We put them in water, don't we? So these solutions are prepped in water anyway, so we're just going to assume that the specific heat capacity is the same as water. Remember that I said to you, if it says it's in Kelvin, who cares? Just make it degrees Celsius, okay? Its density is 1 gram per mil. Why do I need that? I need mass, don't I? So look, if this is 40 milliliters, if this is 40 milliliters and I use the density as 1 gram per 1 milliliter, then what's my mass? 40 grams, right? Milliliters cancels and I'm left with grams. So you have to use the density to give you the mass, right? All right, and then it says, also assume that the volumes are additive. You should know that volumes can contract or expand depending on what they are when they're mixed together. So this is just telling you like, hey, don't worry about it. You can just add these two volumes like I just did and say 20 plus 20 is 40 so that I can come up with the mass of 40. So there's just assumptions here that they have to tell you before you start the problem. All right, so I mix these two things together, and the first thing it asks you is for the net ionic equation, and the second thing is for delta H. Let me be clear as to how you're going to map this problem out. You cannot find delta H unless you find what? Q. And the only way that you're going to find Q is by figuring out your MC delta T equation, but at some point you need to figure out how many moles is your random quantity. Because what do you need to figure out is how many moles per 1 mole for delta H, right? So eventually we have to do a ratio. So this problem is super easy in terms of what's being mixed together. But it could change. I doubt they would do it like this, but you should always be paying attention to limiting reactant. Do I not have two different substances here? At two different molar amounts, right? Meaning, this could be a different number of moles than this is a different number of moles. Like I could have two different mole amounts, which means then I have to choose which one is the limiting reactant, which would then result in only a certain amount of product being formed. Do you agree with me? Most of these problems, I don't know that I've ever seen one that is a limiting reactant problem, will give you identical amounts so that you don't have to worry about that part. So then you just assume that the molarity, the moles is equal on both sides. But I want to point this out to you so that you recognize how this works. When you're trying to find moles, you do X moles over liters. And in this question, I have 0.020 liters, 200 liters, right? And the same thing is true for the other solution. It's X moles over 0.0200 liters, right? So the amount of moles that I have is equal for both of them. And then if you were doing limiting, what would you do? Divide by the coefficient. So that's why writing the net ionic equation is very important for this reaction, so do that first. Do not write this like honors students would. Write this like AP students would. should be very simple. 1 to 1 to 1 coefficients, right? So if it weren't true that these were equal mole amounts, I would have to do limiting. Watch. At this point, I have 0.0200 moles of Ag plus, and I have plus 0.022200 moles of Cl minus, don't I? And so how many moles of product do I form? Don't you dare add them together. Look, it's basic stoichiometry. If there's no limiting, right? If this were limiting, right, you would divide by 1, you would pick which one is smaller. Excuse me, then you would start with the one that's smaller, and you would do this. This is moles of Ag plus, and then you would say 1 mole of Ag plus gives 1 mole of AgCl. Wouldn't you? So then you would just predict that you make how many moles of AgCl? Do we all agree? But if it were a limiting reactant problem, then you would have to predict how many moles you would get. I should just scoot that there so we could see. All right, so we wrote our net ionic equation, which is right here, and now we're going to calculate delta H. So first step is to calculate what? Q of the solution. Then what do you need to find? Q of the reaction, and then you can find delta H. Delta H is always for the reaction, always. What is the solution? The water. The solution is when you mix the two. What happens at the temperature? So be smart before you start. Temperature went? I don't think so. Yeah, so the temperature of the solution went up. So the solution should be endo, and then your reaction should be exo. So let's just solve quickly. You can do this now. What's the mass of the water? 40. Because I added the 2 volumes, right? Now I have 2 solutions that are mixed. I add the volumes, it's 40. C is the specific heat capacity of water. And my temperature change is positive. 40.0, because you added those together, you use least decimals. All right, so let's check our answers. Delta Q of the solution is positive 1270 joules. Did you get that?
Yeah.
What's delta Q of the reaction? Agreed, right? All right, so now we get to the part where we have to calculate delta H. So let's think about this with this idea right here, okay? I have random quantities. How many moles of silver chloride did I form? 0.02. 0.02 moles, right, of silver chloride are formed. What is delta H for? How many? 1 mole. So I have to do a simple ratio. There's lots of obvious ways to calculate delta H from this, but my preference is I do it like a ratio. Part over whole equals part over whole. So if I'm looking for delta H of the reaction, which is always for the reaction, I'm going to say delta Q is for my moles in my reaction, right? My moles in my question. And that's going to be equal to the ratio of delta H per 1 mole. Always 1. Always 1 in the sense of when we calculate delta H per mole, when you literally see the word kilojoules per mole, it's going to be solved per 1 mole, right? But sometimes I can represent like this to you, and that's going to be per mole, but there's 2 of them here. So I would have to calculate that differently. We'll do that like, I don't know, maybe tomorrow we'll look at something like that. But right now, just we're calculating per mole. So I take my delta Q, which was negative what? Negative 1270, right? Negative 1270 joules. And then the number of moles that I use is 0.0200 moles, right? And I do a simple ratio because I say if this is how much heat is being given off for this many moles, then how much heat will be given off for 1 mole? Doesn't that make sense? Just use a ratio. Part over whole equals part over whole. So this is the amount of heat released for my moles. This is the amount of heat released for 1 mole. I'm saying this 15,000 times to you. Listen, stop calculating. I'm giving you this on your quiz. This is the one question that, like, the entire class gets wrong. You just cannot figure out how to find delta H. I don't know why. So this year, I'm saying it a million times to you. When you find delta H, you're going to take your delta Q for your moles and make it a ratio to 1 mole. This is the amount of heat produced for this many. So what's the heat produced for this? The other way I will ask it for you is I will tell you, here's your delta H. Now tell me how much heat's going to be produced for this many moles. And you just go backwards. Do you understand that? It's a simple ratio. So now you solve, and you should get, for this, negative 63,500 joules per mole. But I don't want things in joules because numbers are really big in joules. So it is very, very common, and what is necessary is to represent this in kilojoules per mole. So just a reminder, there are 1,000 joules in 1 kilojoule. So if I put joules here, I divide by 1,000, I move my decimal 3 to the left. That is your answer. Okay.